Okay. Just gonna turn down the music a little bit, and hello everyone, welcome to my first ever video. Today we're gonna be taking a look at Turing Complete, which is a game where you create a PC using logic gates. The reason why I wanted to go over this game is because, well, I find it very useful as a computer engineering student. That would be my background, and I've taken logic gates at university, and I just find that this is a way more fun way of learning, and I really wanted to support this type of game. So without further ado, let's get to it. Congratulations, you have been abducted. Okay, testing you. The rules are simple. Build a functional computer or you'll be eaten. Good luck. So it's quite fun as well with the theme that they have going here. A signal flows from the input to output. Upper left corner. Under input, there's a green icon. Click on it to turn the input component off. Guess this? Yeah. Output is turned off. Signal stopped flowing from the input. Okay. Oh, that's it. Okay, that was really easy. So we're very impressed with how well you completed the last level. That was pretty easy. We have decided you're probably not a plant. Fair. In this level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level, or you'll get stuck in the next level. Okay. Now I do know how the NAND component works. I'll just explain it very quick in case you guys are new to this type of logic gate functionality. So a NAND component is basically actually kind of hard to explain if I don't go over what an AND is at first. But I guess this kind of explains it here. So if you look at it, we have two inputs, right? So we have a red input, we have another red input. Both of them are red right now. If you take a look here, both inputs are red and the output is green. Why that is because you can consider an AND function, an AND logic gate I mean, to be similar to a multiplication. So here we're talking in binaries, so both inputs, if they're red, consider it to be 0, and if it's green, consider it to be 1. So when you have 0 times 0, you get 0, right? And what an AND does is it does the opposite of, it does the multiplication, so it does the AND function, it does the multiplication, and because there's an N in front, the N actually stands for not. So it's not AND, okay? So what happens here is we get the AND going, so 0 times 0 is 0, and because it's not 0, because it's not AND, it's not 0, it will become 1, which is why the output is green, right? I guess we're supposed to fill this out, so will be green. Green times red, so think about it, 1 times 0, what is that? It'll be 0. Because if it's not 0, because of the N in front of the AND, it's going to be also green. And then red times green, same thing, 0 times 1, it's going to be 0, not 0, 1. And then finally, 1 times 1. So 1 times 1 is what? 1. 1, but we have not in front of it, so it's not 1, meaning it will be 0. And that should be correct. Yeah, there you go. Correct, you have unlocked NAND gate. With this component, you can build everything else in your computer. I did not know that. I don't think we took that in class, but I didn't pay too much attention. Now you've unlocked the NAND gate, it's time to build your circuit. Last level you made the table that described the circuit. In this level you build the circuit that matches the table. Not sure what that meant. So they want us to build a NOT gate, which I just explained. Actually, I didn't explain what it was, but I explained. So basically the N represents NOT, right? The important thing here is you want to build a NOT gate. So it means that when the input is 0, it will just make it the opposite, right? So if it's 0, it will be 1, if it's 1, it will be 0. That's a NOT gate. So to create that, unfortunately, 1 second there. Okay, I just realized we couldn't see the NAND gates. I was having the camera bigger while I was there. So we couldn't really see the gates that I was accessing, so I just moved my camera around. So I want to build a circuit that makes the table correct. Click next tick. So, this is next, this is run, reset. Okay. So click the next tick in the upper left corner to test each combination of inputs. You win the level once both combinations have been tested correctly. Okay. So a NAND gate, we know how this, it even shows you, that's cool. Okay. So we know how a NAND gate works, and we want to make a NOT gate. So this just means that when the input goes in here, can I link it? Yeah, okay, cool. So when we only have one input. So when the input goes in, when it's 0, it becomes 1, and then when it's 1, switch it, becomes 0. This doesn't really work. How can I make it from that? Think about this real quick. So, thinking maybe This doesn't make sense. Okay, so think about it very logically. An AND gate, when it's 0, it'll become 1. So we have the first part covered, okay? First part is covered, 0 will give you 1. For it to be 1, we need... for it to be 0, we need it to be positive. Wait, doesn't that just work? That's where I tied it. Why is that always... Okay, if it's green, shouldn't this be 0? Oh wait, maybe I have to do this. Oh yeah, there you go. Oh yeah, that's true. Yeah, if nothing's connected, it acts as 0. Or acts as off, or acts as red. Whatever way you want to say it. So if we check here... There, level complete. Very nice. Oh, okay, there we go. So here we get to take a look at the... Okay, so here we're going to be covering basic logic. That's what I'm going to try and do in this episode very quickly. It's just the basic logic portion. Hopefully we can get through that. Then we do arithmetic, we do memory. It's going to be a lot more complicated. And then CPU architecture. I actually haven't done that yet. Oh, and we get a working computer here. Oh, so this is where we hit the objective. So this is my objective here, is to get the working computer. Then be programming, CPU architecture. So I guess you'd be, programming at a basic level here. CPU architecture, functions. Okay. We'll see what we'll do with the rest, but for now, we're just going to be tackling up until the working computer portion. So maybe split this up into like 3 parts. We'll see. It all depends on how long it takes me. So let's do, I guess, this level. Most creatures on Earth are aggressive and cannot focus. To succeed, you must think logically while not destroying anything. Okay. I think so far we haven't destroyed anything. So what do we create? A NOR gate. Oh, we have a NOR now. Okay, so it seems like what we create, we get access to afterwards. So a NOR gate is just an OR gate, but it's the opposite of an OR gate. So what an OR gate, real quick? Well, it's actually very well explained here. But what I want to explain first is an OR gate. An OR gate is like a summation. So if it's 1 plus 0, you get 1. If it's 0 plus 0, you get 0. But a NOR gate, because there's the not in front of it, right? We'll just invert that. So whatever result you were going to get from an OR gate, you're getting the opposite here. So for example, 0 plus 0 would have normally given you 0, but since it's a NOR gate, you get 1. And it goes on the same way. So 1 plus 0 normally would have given you 1 because an OR acts as a summation. Because it's a NOR gate, meaning not an OR, it will give you 0, and so on and so forth. So let's try and tackle this one here. Oh, we have 2 inputs here. That's nice. Makes sense because it's a multi-gate, it's a NOR gate. Okay, so how would we do this? Thinking, because we have the NOR portion, it's OR, right? Also, if you notice here, if I look at the AND quick, here, I'll click away. It's green, red, red, red. And if you notice, it's the same pattern for both sides. But if you look at the NAND here, it's green, 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 red. Literally the opposite of it. So what I'm thinking is we put 2 knots in front of this. Hopefully this works. Okay, it did not work. What result is that? It's green, so it did the opposite. Okay, wait. So if our okay, one sec. So if our result was red, green, 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 I think if we just move this over here instead. Let's connect these up. Connect these ones, and then connect this as well. Let's check it again. Oh, that didn't work. So let's see what result we get. So we got the complete opposite. So we got red, 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 green. And what did we get here? We got red, 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 green, and then what this was red, green, green, green. What if I just add a knot here then? It will invert everything, right? Perfect. Okay. So we take a look at what we created. So we have 2 knots in front of the NAND, and then 1 final knot after the NAND. Is there like an answer? Yeah, the solution. Let's see here. Oh, I have to open it. Okay. Well, like we got it correct. So I was just seeing if there's a more optimal way of doing it. Let's go into the level map. Let's try this. should be happy you get to participate in our glorious test. So I have to say this alien kind of looks like a Rick and Morty character. You get a chance to communicate with very advanced people from the galactic civilization. See, this is why I wanted to showcase this game. It makes teaching, or like it makes learning, I mean, very, very fun. So I'm glad to be able to play this. It's a great way of learning, honestly. Input 1, input 2. So what do we have? Oh, we have an OR gate. Okay, so that should just be what we just did minus the null at the end. So if you like here, boom, 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 boom. And if you want to like think about it like more in the sense of like why does this work? If you look at the NAND gate, it's green, 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 red. Like it's the same inputs on both, right? Green, green, red. We have red, green, green, green. What we do by putting a not in front of it, it means that every time it does the check portion of it, so when it checks for these inputs, it just inverts the inputs, right? So if you look at it from right side to left side here, it's green, 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 red, which if you look here is green, 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 red. So by putting the not in front, we get this desired output. Hope that makes sense. Keep skipping it accidentally. There you go. So we unlocked the OR gate. So I think okay, for some reason we can't use it yet. Right now the elephant is dominating all the other test subjects from adjusting for brain size. You're also doing well. I doubt that the elephant's doing that well. We have an AND gate. Okay, so this is what I just talked about. So something you need to know as well is that if you put two nots in front of each other, it's just gonna act as if there was no not at all, right? So by having a NAND, so we want an AND gate, and we have a NAND, right? So we put the NAND into a NOT, we just get AND. Like there's not much more to think about here. I guess we could probably look at it from this perspective as well. So here we look, it's green, 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 red. I'm looking at the output here, right? So the output is green, 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 red, and the output is red, 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 green. So it's literally just the opposite, right? Let's try it out, and there we go. Let's see here, always on. Okay, so we've moved past basically all the logic gates. There's also like an XOR or XOR and XOR, stuff like that. Those are a bit more complicated. I don't know when we'll see them exactly, but these are the basics that we have here. Oh, we have everything now. NOR, NAND, OR. That's okay. That's nice. Create a circuit that is always on. So what would be always on? Meaning that I think an OR would be useful here because. Wait, one sec. What's already basically most of the time on? An OR. An OR is basically most of the time on. Can I delete this? Oops, it's just there. I saw there's a there's a sec too. Okay, that worked. Back. So we have an OR here. So we want something that's always on. So an OR is basically always on as long as one of them is 1, right? So we put like a not here and then collect it. So it means that even if the output is red, it will make this one green, making the OR correct. And if the output is green, well, it doesn't even matter because 1 and 0. I think this should work. Alright, perfect. And so unlocks your first manual bit. This one's important. Make sure you understand it. Okay. Oh, this is de Morgan's law. So we also took this in university. You guys could read through this, but it kind of emphasizes what we just did together. So you can get any of these. Like you can get an OR with an OR, and you can get a NAND with an OR. You can get an AND with an AND, etc., vice versa. Like it goes all the way around. So I'm just gonna read this first part. The truth table of the 4 fundamental gates are symmetrical. So if you're wondering what a truth table is, it's this portion right here, meaning based on the input, what output do you get? And you'll notice that these 4 are all the possible inputs. So when we have 3 inputs, for example, you're gonna see this is gonna be a lot longer. So it's gonna be like, I think it's 2 power 3. That's how many like different input possibilities we'll have. Whereas here we only have 2 power 2, which is why we only have 4 input possibilities. Okay. Going back to it, so these gates are all symmetrical in the sense. So you can convert between them by inverting the input by vertical arrows or inverting the output, horizontal arrows. So inverting the input, so that means if we put NOT gates, remember the NOT gate? So that's what I mean. Oh, I kept saying opposite. I guess invert would be the more correct word. So if we put NOT gates in front of these ORs, we would get an AND. And right, inverting the input for vertical arrows, yeah. And if you put a NOT gate at the end, well, it makes sense. If you put a NOT gate at the end of the OR, you'll get a NOR. So it makes a lot of sense. You put a NOT gate in front of an OR, you get a NOR, which is what? A NOT OR. You put a NOT gate in front of an AND, and what do you get? You get a NOT AND. And vice versa, because you remember NOTs can cancel each other out, right? So if it's NOT AND, and you add another NOT, it'll be NOT AND. And if it's not an AND, it will be just an AND, right? So that's kind of what gives us the results here. And yeah, I think it's pretty self-explanatory. I'm just going to give you guys a moment to read this if you care too much about it. And let's go on. Okay. Second tech. As you know, these tests culminate in building a functioning computer. Yeah, that's why we're here. Species that are capable of finishing are considered sentient by law. That is interesting. This is the main reason we don't eat you afterwards, so we definitely want to get this done. Let's see here. So, second tick. What is our objective? I don't get it. Did they mention what the objective was? Double log. Oh, okay. Output green on the second tick only. So I don't know how. I don't understand like the tick exactly, like what a tick represents, but it's obviously the second input possibility. So we just want it so that when it's green red, it gives us a green, but otherwise it'll be all red. So start off with something that's mostly red, like a NOR, or let's start with a NOR. Why not? So a NOR, for example, gives us mostly red. So what we're going to do is we're going to change this portion here. Now we know that a NOR, if we look at a NOR, it's only green when both inputs are red, right? So both inputs are red here. We want this to be red when both inputs are red. Meaning that, okay, one sec. Okay, I think I solved it. So here, when this one is 1, because remember, green is 1, red is 0. It's just like the better UI for the game. So when this one is 1 and then this would be 0, we get green, meaning that in the case of the NOR, I'm sure there's many other ways of doing this, but in the case of the NOR, we would need to make this input into red. So we would just add a NOT gate up here. And in the first input, it's like the first one where both inputs are going to be red. Here, I'm going to test it actually for you. So if we make both inputs red here, you're going to see that the output's going to be red because one of them is green, right? And here, let's test it. So if we make one of these green, it is green because this will invert it. Okay, I think we're good. So let's check it. There, nice. Not sure how that corresponds to a computer, but that's what we're here to learn. And turn down the music just a tiny bit. I feel like it's a tiny bit loud. I do like it so far, though. Let's turn on this as well. Okay, let's keep going. Last time we built a circuit that was always on when we were at the second tick, or always 1 or always green, right? This level will build a circuit that is green when we are at the second or third tick. So both of these. This is also known as an XOR gate. Oh yeah, okay. So that's an XOR gate. Honestly, I didn't do too well with XOR gates, so we're gonna see how this one goes. It's difficult. This level is difficult, so don't be discouraged if you don't get the answer right away. Okay, I think we're gonna start with the same thing with a NOR. We know how this works so far. Actually, logically speaking, a NOR can't be the solution, right? Because if you look at a NOR, it's only green when both are red, and I can't make both red in both of these situations. It just doesn't make sense. Unless maybe I use like an AND gate before or something like that. I'm just speculating right here, so let's try and think backwards for a second. So we're trying to. So a NOR is green when both of its. So let me just make sure. Yeah, NOR is green when both of its inputs are red. So we just want it so that we have something that when this happens, when it's 1, 0, the inputs, we get red. And same thing here, right? A NOR is. Oh, we need double red. I don't think that matters. We can just link it up to both of these. Let's remove you and put this. You think this would work? Yeah. Almost. Just missing the inside portion. Anyways, so I'll get back to it when I'll see you guys again when I do figure it out. So just give me a moment here. So hello everyone, welcome back. I think it took me around 7-8 more minutes, but I figured it out. I don't think this is the optimal way of doing it, but it's the way I figured out. So I was thinking about it in the sense of, I don't know where we left off exactly, but as you know, the XOR gate is when all inputs are red, we want it to be red, and when all inputs are green, we want it to be red. So basically, if the inputs are the same, we want the result to be negative, and if the inputs are different, we want the result to be positive, right? So how I thought about it was looking at the NAND. Well, actually, I looked through many different options, but like mainly the AND, when I was looking at the AND here. AND is negative if there's any difference, right? So if it's green, green, it's green. But if there's any difference at any point, it just goes bad, right? So what I thought of is basically I just thought of it in the sense of like, what output can I have? So what I was trying at first, I'm kind of losing you guys probably. What I was trying at first was I was trying to have double NAND and then an AND at the end or an OR at the end, but none of those worked, unfortunately. And by observing the NAND, if you look at the output, it's green, 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 red. And if you look at the OR, it's red, green, green, green. So I just thought, okay, we have a beginning green and we have a beginning red. So that will give negative in an AND. And then we have an ending red and an ending green, which will also give negative in an AND. And they share green in the middle. So basically what I did is I just looked for what shares green in the middle. So I found these two. I think, yeah, these two made the most sense. Well, actually, they were the only two who shared green in the middle. And I just finished it off with an AND. Maybe I could have finished it off with an... Nah. Like, you could technically finish it off with an OR, but you'd have to put a not at the end of it, I think. Or before it, one of those two. But either way, I believe after it. But either way, this is the solution I came to. We're actually going to take a look at what the solution could have been.
This level has two.
Oh, they explain it and everything. Damn, that is very fun. We're just here for the results. Oh, so yeah, they actually did the same thing, but did they? Oh yeah, they did. They just made it more obvious that the inputs are separate. I kind of have it mixed and matched here, in the sense of it kind of looks wonky here, but here I'll just show it to you just in case you're confused. First input goes into the first. First input also goes into the first of the OR. Second input goes into the second input goes into the second part of the NAND, and second input goes into the second part of the OR. As I think that's enough explaining, and let's move on to the next level. Let's do this one. We're almost done with basic logic. So create an OR gate with 3 inputs. And that just be I'm a bit confused, one sec. I just go like this. I kind of feel like it would be this, but like I am not 100% sure. Wait, what I'm doing does not make sense. So then OR gate with 3 inputs. Oh, we have XOR now. I don't think we need it though. Let's just look at this. So just when it's all red. So when all these are red. I'm thinking, wait, okay, let me just do an OR into an OR. OR into another OR. Because if you think about it, when both of these are red, it will give you red. And then this is also red, so we'll go all red and boom. And then if one of these is green, it'll give you green, and this will just act. Okay, I think this actually works. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so as I said, 2 power 3. When you have 3 inputs, it's 2 power 3. Before we only had 2 inputs, so it's 2 power 2. And that's how many like input customizations were possible, right? Let's do here. Create an AND gate with 3 inputs. So I imagine it'll be very similar, so let's not waste any time. It'll be an AND into an AND again. Let's try this here. Oops. There we go. Let's test this out. Perfect. I was honestly a bit worried it was not going to work. So that's just a bigger AND gate, so I'm guessing I'm going to have access to those now. We're almost done, so this will be the last level of this episode. Create the inverse XOR gate known as XNOR. Very simple stuff so far. So we just take an XOR gate and we want to inverse it, right? So to inverse it, we put a NOT at the end. If we invert the inputs, it's not the same thing. I don't know what the term would be for it, but this is what an XNOR gate looks like. And that is all the levels in the basic logic section. So in the next episode, depending on how difficult these are, they're taking the memory. I think they're going to be a lot more difficult, and this might have to be split into different parts. I'm trying to make every episode around 20 minutes. Yeah, so in the next episode, we'll try and tackle these levels, and yeah, see you guys in the next video.